And transverse modes correspond to the spatial distribution of the field inside the resonator. There is some ambiguity in this term. So whether we speak single mode or multi-mode, because if we don't specify which mode we mean, either spatial mode, so transverse mode, or longitudinal mode, then this term single mode or multi-mode makes no sense. So please remember that the longitudinal mode is the standing wave which is existing inside the resonator, right? So we have the resonator and we have a standing wave inside. So this is a longitudinal mode. So there might be many longitudinal modes in the laser, and the frequency of these modes will be will differ between consecutive modes by the value called FSR, right? So this is C/2L, the free spectral range, right? So the longitudinal modes are all the frequencies that can exist in this resonator. So the number of modes will depend mostly on the bandwidth that is of the gain medium, which is inside the laser. So the broader the gain bandwidth of our medium, the more longitudinal modes we can have, because they will be supported by this gain. So already we have seen like the examples of, for example, gas lasers like helium neon lasers, where the gain bandwidth was quite narrow, and we had only a few longitudinal modes in the laser, like sometimes 1, sometimes 2, 3, 4. Or on the other edge, we had the example of the titanium sapphire laser, of which the gain bandwidth was at the level of few terahertz, right? Tens of terahertz bandwidth, while in the helium neon, this was gigahertz, 1.5 gigahertz, right? While here we have tens of terahertz. So if the mode spacing is like 100 megahertz, for example, then we will have only few modes here, but millions of modes here. So also the FSR of the cavity will influence the number of modes, because if the FSR is smaller, then we have more longitudinal modes. Of course, this can be also limited by the mirrors of the resonator or any kind of filtering. So if the laser is generating one longitudinal mode, then we can say that the laser is a single frequency laser or a single longitudinal mode laser. But this is a very special case where there is only one frequency emitted by the laser, which means that there is only one standing wave inside the resonator. So in general, these longitudinal modes on the frequency axis will look like that. So when we have the length of our empty resonator, these modes start from 0 and they span up to infinity, because we have an infinite number of potential resonances of our resonator, and they are spaced by FSR, which is C/2L. But if we add the gain medium inside our laser, the gain medium will have a certain bandwidth. So it will cause that some of the modes will be excited in the laser. So here, if you have with this this Gaussian, this Lorentzian curve shows the envelope of the gain bandwidth of the gain medium. So you see that only the few modes that are under this gain curve will be excited by the gain medium, and the rest of the modes will not appear in the output spectrum. Of course, if they overcome the losses, right? Because we have some losses because of the reflectivity of the mirrors. So we have some level of losses. So as you can see, there are two modes that are actually under the gain curve, but the gain is not compensating the losses. So these modes will not be excited. So this particular laser will have 3 longitudinal modes. So the spectrum of this kind of laser here on the bottom of this one will look like that. So if we look at it in the frequency or the wavelength domain, we will see 3 lines. And this is an image that you probably have seen on the laboratory where you analyze the spectrum of a helium neon laser. Probably there are some more lines visible there, but in our case here we have 3 longitudinal modes. So to summarize, a single frequency laser will generate only 1 longitudinal mode. So we already discussed the possibility how to do that. So we can either design our cavity to have a very large mode spacing, so a very large FSR in comparison to the width of the gain bandwidth. So this is something that can be done in case of a helium neon laser, where the gain bandwidth is at the level of 1.5 gigahertz. So if we make the FSR like at the level of, let's say, 750 megahertz, then we have the situation in which only 1 longitudinal mode will be present under the gain curve, because the other 2 neighboring modes will be too far away, right? So 750 megahertz is the it should be more than 750 megahertz mode spacing. Or the other possibilities include filtering. So if we have more modes, we can apply some filtering mechanisms to filter out only the mode that we are interested in. What about the transverse modes? So the transverse modes are they are related to the distribution of the electric field, which is inside the resonator. So this is the distribution of the field that is reproducing themselves after 1 round trip of the resonator. So this translates to the shape of the output beam, which is described with this TEM number. So we already discussed that. So this here is the fundamental TEM00 mode, and the other distributions are the so-called higher order modes. And the TEM00 fundamental mode is called the fundamental mode, which is actually a Gaussian beam, and it is described by the all the mathematics that we were already discussing during the lecture about Gaussian beams. So we need to distinguish the types of modes, so either longitudinal or transverse. So the longitudinal are related to the frequency of the light that is inside the resonator, while the transverse modes are related to the distribution of the field. So a single transverse mode laser will generate a fundamental TEM00 mode, a Gaussian beam, while a single longitudinal mode laser will generate only 1 optical frequency. So that's important. So this might be confusing, but generally a laser can generate many longitudinal modes, so many frequencies in 1 single transverse mode. So we can have a TEM00 beam, which is a single transverse mode, but it will contain many longitudinal modes. So this is also the case of, for example, the helium neon laser, which is single mode in the transverse sense, but it might be multi-longitudinal mode. So this is what you see on the laboratory, where you have where you analyze the mode structure of the helium neon laser, and you can see that it has many longitudinal modes, like 4 or 5 modes. But if the laser has many transverse modes, you need to remember that each transverse mode will have a different frequency. So will be actually a different longitudinal mode. So this image here shows an example how a multi-mode and a single mode laser spectrum will look like. So this is a classical example of a single mode, single frequency spectrum we have only one line in the spectrum of our laser, and the rest here is the noise. So you can see we analyze this in a very broad range of spectrum, so between 1030 nanometers and 1060, and we see only one pronounced peak with a very high signal to noise ratio here, which means that the laser is single mode. Here on the right hand side, you can see many lines, many peaks, which means that the laser is a multi-longitudinal mode laser. So when we speak about modes, I will now switch to the main topic of today's lecture, so the pulsed lasers. One of the technique of making a pulsed laser is called mode locking. So it's a technique where we synchronize the phases of the longitudinal modes that are oscillating in the resonator. Because generally, if we look at the modes oscillating in the resonator in case of a continuous wave laser, we will see that the modes have random phases. So there is no fixed phase relationship between consecutive modes. They, of course, differ by the same frequency. So, for example, the difference between the frequency of the mode number, let's say n, and the mode number m will be equal to FSR. So this is C over 2L. So the frequency difference between the consecutive modes is constant, but the phase might vary. So if we have no fixed phase relation between all the longitudinal modes, and when we have many longitudinal modes in the laser, they will just sum up. So the fields will just add together, but if there is no fixed phase, the interference between all these modes will be just incoherent. So this will be just an incoherent sum of all the intensities of the longitudinal modes that are oscillating inside the resonator. So on average, this will sum up to a constant output power, which we call continuous wave, CW. So the same applies to the single frequency laser. So when we have a single frequency laser, we have only one standing wave oscillating. So we have only a constant power at the output. But when we have like 1,000 or millions of modes that are oscillating and they have random phases of this oscillation, then the output will be a continuous wave. But if we somehow force the modes to have the same phase, then they will interfere with each other. So we already know from the example of the Michelson interferometer, for example, that when the two beams of the Michelson interferometer are in phase, so that the phases of these two beams that are divided here in this Michelson interferometer are matched. So we have same phases here. We will have constructive interference, right? So because the phases are the same, these two waves will coherently add together, forming a beam with increased intensity, right? So the interference in case of the mode lock laser, well, where all longitudinal modes have the same phase, this will lead to constructive interference between all these longitudinal modes. And this in turn will lead into the formation of a pulse inside the resonator. How? Yeah, this is explained on this image. So this is the case where we have locked phases of the longitudinal modes. So you can see that all these modes have different frequencies. So you can see here that the frequencies of these oscillations are different, but the phase is the same. So if the phase is the same, so it means that there is one point in the oscillator, in the resonator, where let's say the peaks of these waves, they all overlap in one spot of in time and in space. So if we would now add all these electrical fields here that we see here in this resonator, and we would just sum up these intensities, we will see that all the modes here will sum up to something which is close to 0. But here we will have a high intensity pulse, because when we sum up these intensities, this will be a pulse. And then again, we will have 0 intensity here. So it means that we will have one pulse that is circulating in this resonator, bouncing between these two mirrors. So at the output, we will obtain a pulse, a short pulse, or actually I should say a pulse train. And the pulses will be separated by a distance that corresponds to the round trip time of the pulse through the resonator. So this will be 2L over C, where C is the speed of light, right? And L is the length of the resonator. So this will be the inverse of the mode spacing of the FSR. So in the time domain, this pulse to pulse spacing is equal to 1 over FSR. So this is the inverse of the mode spacing. And we call this value the pulse repetition rate. Okay, so this is the repetition rate. So it corresponds to the round trip time of the pulse inside the resonator. You can see it on this, also on this animation. I hope it works fine and you see it through Zoom. So this animation shows you an example with 5 longitudinal modes. These modes have different frequencies. As you can see, they oscillate with different frequencies. They have different amplitudes and they have the same phase. So they are oscillating in phase. And on the bottom here, this is the sum of these oscillations. So this resonator here shows you the live animation of the pulse formation. So this image on the bottom sums up all these 5 modes. So you can see that already 5 synchronized modes that will just oscillate with the same phase produces something which looks like a pulse. Because as you can see at the output, we have pulses, right? So you can already see that even 5 modes can create a pulse, and you can, I think, intuitively guess that the more longitudinal modes we have synchronized in our laser, the shorter pulses we can get at the output. I think I can show you another animation, another video that describes the principles of mode locking, but this is a completely non-optical example, but yeah, I will play the movie. So as you can see, we have a set of pendulums, and each pendulum will represent one longitudinal mode of the laser. Okay, and as you can see, all these pendulums, they have different frequencies because the length of these wires was different, but they have the same phase because, as you saw, the guy started all these pendulums at the same time, so they have the same phase, but they all have different frequencies. And as you can see, at some points, you might think that this movement looks very chaotic, so that it makes no sense. But after some period of time, which is in this case approximately 40 seconds, this setting will go back to the initial setting. So it means that we generate a pulse. Yeah, so you see that now. Yeah, now they came back to the to the same setting that was on the beginning. And this will repeat once again, right? So this is a representation of oscillating of the modes inside the resonator. You can see another example here on this animation. So on the bottom here, you can see this is the resonator, the representation of the resonator. So we have two mirrors and the gain medium, and there is only one pulse that is circulating in this resonator. So we have one pulse that is bouncing between these two mirrors. And on the top here, you can see the longitudinal modes of the laser. They have different frequencies, and the difference between them is equal to FSR. But they have the same phase. So you see that if they sum up, they create a pulse which is just traveling between the two mirrors. So in this case, you can see just a negative or positive field because this is the electric field. So normally we see the intensity, which is the square of the square root of the, the square of the electric field. So we will see only the positive part, but here this animation shows the electric field. So at the point where this pulse hits the output mirror, this output coupler, just a small portion of light is extracted from the resonator because the output coupler can have a reflectance factor of, let's say, 90%. So it means that 10% of the power will be transmitted. So it means that 10% of the power of the pulse will be outcoupled from the laser, and this will create our output, and the rest will stay in the resonator and be amplified again. Yeah, and as I already mentioned, if we have more modes synchronized, we can have a shorter pulse. So if we look at a simple case where we have two longitudinal modes which are synchronized in phase, if we interfere two longitudinal modes together, we will see just the beating. So we will just see a sinusoidal beat note between these two modes. But if we add more and more longitudinal modes, we will see that this peak, the pulse is getting shorter and shorter. So the more modes we add, the pulse is getting shorter, and the intensity is growing. So you see that here we have the same scale. So when we have two modes, the intensity reaches 4. When we have 3 modes, it reaches 9, then 16, 25, and so on. And if we reach the number of 100 synchronized modes, we have the intensity 10 to the 4th. So it means that if we synchronize the phases of a larger number of longitudinal modes, then we have a shorter pulse and a higher intensity, higher peak power here. And we can actually go up to really short pulse durations. So this is the difference between the optical spectrum of a single mode laser and a single frequency laser, which is operating in the continuous wave regime. So this is just a continuously working laser. So we see on the green image, we have one pronounced peak sitting on some kind of background resulting from the noise. Those who already had the exercise with the erbium doped fiber amplifier should recognize this shape of this noise because you measure it on the laboratory. But if we synchronize the modes of the laser, we will not have a pronounced peak, but we will just have a very wide spectrum with a very smooth envelope. And under this envelope, if we would look closer under this envelope and see, take a look with much higher resolution, we would see discrete individual lines that are corresponding to the single longitudinal modes of the laser. So to summarize the main features of the mode-locked laser. So the mode-locked laser will emit a train of equally spaced, very short pulses. So it's important to remember that these pulses are identical and they are equally spaced. And they are spaced by the resonator round trip time, which is the inverse of the free spectral range, or the repetition rate. So we very often rather express this in the frequency domain. So we rather say that we have a repetition rate rather than separation in the time domain. So the output spectrum of a mode-locked laser is very broad. So it might span over tens or hundreds of nanometers. So tens of terahertz in the spectrum, in the spectral domain, the frequency domain. And the broader the spectrum, the shorter the pulse. You can see it on this image, on this animation, that if we broaden the spectrum, we shorten the pulse. And what is important is that this relation between the pulse width and the spectral width is fixed, because we have a parameter which is called the time bandwidth product, which is the product between the pulse duration and the spectral width, the bandwidth, and this is constant. So if we increase the bandwidth, then we can decrease the pulse duration. So if you want to decrease the pulse duration, if you want to make a shorter pulse, you need to have more bandwidth. So this is the physical limitation, that we cannot have pulses shorter than resulting from this equation. So in case of lasers, this is usually equal to 0.315. Yeah, and the third feature of a mode-locked laser is that in the frequency domain, if we look at the output in the frequency domain, it consists of multiple individual lines, narrow lines, and it has a kind of a comb-like structure. Because if you would make a Fourier transform out of a pulse train in the time domain, you will get a pulse train in the frequency domain. So a Fourier transform of a train of Dirac functions in the time domain corresponds to a train of Dirac functions in the frequency domain. So this is a mode-locked laser. But the main question is how to actually achieve this state that we have these phases synchronized, right? So how to force the laser to have this situation where the phases are locked, so that all longitudinal modes have the same phases. So it turns out that this is relatively easy. There are many ways to obtain this synchronization of phases, but in general, we need a mechanism or a device which is called a saturable absorber, which we place inside the resonator. So you can see here schematically a resonator which has the saturable absorber. Besides that, we have, of course, the gain medium, and we have two mirrors. One of the mirrors has 100% of reflectivity, and the other mirror, which is the output coupler, has a reflectivity of less than 100%. So we have a portion of light extracted from the resonator. And we insert this saturable absorber here. So what is so special about this saturable absorber? So it's kind of a device which has a nonlinear transmission function versus intensity of the incoming light. So this nonlinear transmittance curve looks like that. So it means that the transmission of this material or this device increases when we increase the power that we apply to this device. So normally you would say that any material will have the same transmission ratio expressed in let's say percent, right, versus power. So it shouldn't matter if your material has, let's say, 50% of losses. It should have 50% regardless of the power that you put on this material. So if you use very low powers or high powers, you should still have the same losses. But in case of the saturable absorber, it turns out that at low intensities, the attenuation is higher. So we have less transmission. So we have very low transmission through this material. So it absorbs light with very low intensity. However, on the other hand, it transmits light with high intensity. So it will favor the existence of high intensity in the resonator. And we define three main parameters of the saturable absorber. So one is the modulation depth, here delta T, which is the difference between the on and off state. So the difference between the transmission at low intensities and the transmission at high intensities. The second parameter is the non-saturable loss, which is just the intrinsic loss of the material that we cannot saturate, and the saturation intensity. So this is the kind of a threshold where we say that above the threshold, our absorber is saturated, or below the threshold, it's not saturated. So what will happen if we put such a device inside our laser? It will happen that we will modulate the losses inside our resonator, because the saturable absorber will suppress any kind of noise or low intensity emission from the gain medium, but it will less attenuate pulses, because pulses, as we already said, a pulse has a much higher intensity than the continuous wave emission. So if the pulse has a higher intensity, it will pass through the saturable absorber and it will experience less attenuation, okay? But on the other hand, if we have any continuous wave radiation or some noise or low intensity radiation in the resonator, it will be attenuated by the saturable absorber. So if we insert such a device into our resonator, we will modulate the losses. So this graph shows the evolution of the gain and the losses and the output of the laser in time. So when we start our laser and we pump it, so we deliver energy to the laser, we will have some constant level of gain and some kind of losses that are, in this case, higher than the gain, because we have the saturable absorber. So the saturable absorber will absorb all the the noise and the spontaneous emission that is occurring in the laser. But at some point, the saturable absorber will saturate, because we will have some situations where in this noise in the laser, there will be some kind of, let's say, like a small bump that will have a higher intensity than the background, right, of our laser. So this small peak will be transmitted through the saturable absorber, and it will exist in our resonator. So at some point where we have this pulse created in the laser, the pulse will saturate the saturable absorber, so it will pass through it. So the losses of the saturable absorber will suddenly drop. So the losses of the entire cavity will have a minimum here. So we will emit a pulse, because here in this region, the losses are overcompensated by the gain. And then we have some kind of regeneration, so some kind of time where the saturable absorber gets to its initial state, so it blocks again all the radiation that is present in the resonator, and then again we have a pulse. So this is a repetitive process. So generally, the saturable absorber will block any continuous wave radiation which is present inside the resonator, which generally means that this saturable absorber will force the laser to synchronize the modes, because there is no other way to pass through the saturable absorber if the phases are not synchronized. So since only high intensity pulse can pass through the saturable absorber, the laser has to synchronize its modes to pass through the saturable absorber without losses. And this process is starting from noise, as I said. So at the beginning, we have noise in our laser because we have just only spontaneous emission. But it might happen that there are some spontaneously generated peaks in this noise. So this peak of the noise will be transmitted through the saturable absorber, and in the next round trip, it will be amplified, and again it will experience less losses when it will pass the saturable absorber. So when we have again another round trip, then this will be amplified again more and more and more, and after tens or hundreds of round trips, we will obtain a steady state in which we have only one well-defined pulse in the resonator, and then we will have a transient behavior, as you see in this image, where the pulse will cause that the saturable absorber opens and transmits the pulse. So I hope this is clear to you. If you have any questions, then of course you can interrupt me and ask. So everything's clear. Okay. So there are many types of saturable absorbers. I will not go into the details here, but we generally distinguish two main types of these absorbers. So the first is called real saturable absorbers. So these are just materials or physical components that have the property of saturable absorption. So of this nonlinear behavior of the transmittance of or absorbance versus the power, right? So these might be semiconductors. So this is the most popular saturable absorber, so-called CSAM. This is a semiconductor which has this property. But there are many other types of materials, for example, based on carbon, that have these properties. And there is also a group of so-called artificial Sato-Rabo absorbers. So these are basically nonlinear effects that occur in optical fibers or in bulk media that have also this property. Because as you might already know, all the nonlinear processes occur at higher powers, and the same applies to optics. So at high powers, the optical materials will start to behave in a nonlinear way, and we can exploit these nonlinearities to obtain this behavior of a Sato-Rabo absorber. So we distinguish several types like nonlinear polarization rotation, nonlinear loop mirror, or so-called Kerr lens mode locking. There was a question on the chat: would it be possible that lasers synchronize on more than one peak? So you mean more than one pulse at simultaneously circulating in the laser? Yeah, that's a very good question. This is possible. This is possible, but in most of the cases, this is not unwanted. This is unwanted, but it happens. Maybe I will use this board. So generally, when we have this resonator, and we have our gain medium, and we have our Sato-Rabo absorber, in normally you have only one pulse that is moving around this resonator, right? But it might happen that you have so-called harmonic mode locking. And in harmonic mode locking, you have more than one. You can have, for example, two. And in harmonic mode locking, they are also equally spaced. So in harmonic mode locking, you have a situation where you have the resonator, and when you have one pulse traveling this way, then you will have the second pulse here in this point. So they have the same spacing. So at the output, you will see just pulses with the repetition frequency, which will be doubled. So you have twice FREP, despite the fact that you have the same FSR, you have the same cavity length, the same mode spacing, right? So you have twice the FREP. And this is called harmonic mode locking, and this is possible. In some cases, you can have more pulses. I don't remember what is currently the world record, but in some experiments that we done here, we had a few hundreds of pulses synchronized in the resonator. It also might happen that they are not equally spaced. For example, they can travel as a pair of pulses, which are so-called bound pulses. So we have two pulses which are separated by some picoseconds, and they are circulating with the spacing of let's say some nanoseconds between these two bunches of pulses. Yeah, but this is of course possible. So that's a very good question, and it happens sometimes, but usually we want to have the state where we have only one pulse. Okay, so I will go further. Okay, so this is yeah, the slide where I stopped. So here you can see an example of a mode locked laser, a setup of a mode locked laser which is mode locked with a semiconductor saturable absorber. So the CSAM. So you can see the arrangement of this laser. This is a laser, solid state laser based on ytterbium doped calcium fluoride. So you see here is the doped crystal, the doped medium. The pump that was used is a laser diode. So you already know that the best laser diode to pump ytterbium is the 980 or 976 nanometer wavelength. And this CSAM here acts as this very fast modulator that provides the output pulses. So here you can see the pulse shape, and the pulse duration in this case was 65 femtoseconds. So generally, it's worth to say that these mode locked lasers can generate really short pulses. And this is the top image shows the optical spectrum. So the mode locking mechanisms that I was describing, they are called passive mode locking. So this is passive mode locking. Passive because we do not actively modulate anything. So we don't drive these devices with anything. These are just passive modulators that just modulate themselves by triggered by the light, right? So this is called passive mode locking. However, we have also a method which is called active mode locking, where instead of the saturable absorber, we can place an actively driven modulator, which we just drive with the frequency, which is the which can be synchronized with the mode spacing of the laser. So, for example, if our laser has the length of L, which would be 1 meter, this will correspond to the mode spacing of 150 megahertz. So if I want to actively mode lock my laser, I need to insert a modulator. This might be a acousto-optic or electro-optical modulator. So you already, I think you already had the exercise on the laboratory with acousto-optic modulators or electro-optic modulators. So I would need to drive this modulator with the frequency of 150 megahertz. So I can synchronize my losses of the cavity with the frequency of the, or let's say with the round trip time of the pulse inside this resonator. So this will also force the pulse operation and synchronization of the modes. And here, this also somehow corresponds to the question that you asked. I can increase this frequency, for example, to 300 megahertz. That's why this is n times delta f here. So I can multiply the frequency that I am using here, so I can multiply the number of pulses because I can increase this modulation frequency. However, this needs to be an integer number that multiplies the repetition, the mode spacing of the laser. So in active mode locking, we need a modulator. So we need an active device which we will have to drive with an external signal. So we need an external generator. On the other hand, we can tune the repetition rate because we can multiply it by n. And the main difference between passive and active mode locking is that active mode locking provides longer pulses than passive mode locking. So please remember that active gives longer pulses than passive. So passive is always shorter, because the response of the modulator is much faster in the passive case. So in the active mode locking, you can get pulses generally longer than 1 picosecond in duration. But with passive, you can go down to few femtoseconds, so much shorter pulses. Yeah, so we also can think about the possible pulse duration that can be generated from these kind of lasers. So generally, the physical limit is the so-called single cycle. So single light cycle is just one waveform, right? So at a given wavelength. So let's assume that we have the wavelength of 800 nanometers, laser at this wavelength. So the light will travel 800 nanometers. So from here to here, so this is 800 nanometers, right? The wavelength. So light travels at the speed of light, see? So to travel from here to here, light needs 2.7 femtoseconds. So the shortest possible pulse at this wavelength is 2.7 femtoseconds, because this is a single cycle. So if you want to go to shorter pulses, so for example, if you want to generate 1 femtosecond pulse, you would require a wavelength of 300 nanometers, so a much shorter wavelength. That's why the shortest pulses, even attosecond pulses, are generated in the X-ray regime. But in general, if we consider passively mode-locked lasers, usually we can get pulses shorter than 100 femtoseconds easily. In some of the cases of solid state or fiber lasers, you can go down to maybe 30 femtoseconds. And there exists some lasers that can generate also single cycles. But generally, you should remember that passive mode locking enables us generation of very short pulses at the time scale of femtoseconds. So tens or hundreds of femtoseconds. And femtosecond is, of course, 10 to minus 15th of the second, right? So it's a very short event in time. And basically, they are generally, laser pulses are the shortest events that exist in nature. So there are no shorter events in time that could exist. So in humans, there are some chemical reactions that occur in the time scale of maybe 200 femtoseconds, but in the eye, in the retina of the eye. But the laser pulses can last for a couple of femtoseconds, which is an enormously short time. So you can think about how to actually measure the pulse duration of such a short pulse. So the general rule of making any kind of measurement is that if we want to measure something, we need to have a measurement device which is more accurate than the value that we want to measure. So for example, if you want to measure like the length of something, like you want to measure, let's say, height of a person, which is 1 meter and 80 centimeters tall, then you just need a ruler, like the ruler that I have here. I hope you see it. Like I have a ruler, and it has a resolution of 1 millimeter, right? So it's completely enough to measure someone who has 1 meter 80 centimeters with a ruler which has 1 millimeter of resolution. But with this ruler, I cannot measure something which has 100 micrometers in the dimension, right? Because the resolution is not enough. if I want to measure something which is 100 micrometers, I will anyway see, I could anyway read only 1 millimeter, right, on my scale, on my ruler. So in the let's say not optimum, but the minimum required resolution, or my measurement resolution, is the having exactly the same duration of my reference. So in case of lasers and measuring laser pulses, we can use the pulse itself to measure itself, and this is so-called autocorrelation. Why we do that? Because someone may say, yeah, we have a photodetector. Why can't we just take a photodetector and shoot the pulses into the photodetector, and we will just read out the electrical signal at the output of the photodetector, and this is great. Probably you haven't seen oscilloscopes that could resolve pulses at the femtosecond scale. So usually an oscilloscope has a bandwidth of hundreds of megahertz, maybe few gigahertz, maybe tens of gigahertz. However, maybe 10 gigahertz oscilloscope can resolve a pulse with a duration of 50, 60 picoseconds, right? Also, photodetectors are relatively slow devices because there is a response of the photodetector, of the semiconductor, we have the amplifiers there, and so on. So the rise time usually of a photodetector, which can have like the bandwidth of 30 gigahertz, which is an enormously high bandwidth. So the rise time will correspond to about 30 picoseconds. So if we take a femtosecond pulse and direct it to the photodiode, shine it on the photodiode, and we will read out the signal, this will translate into a picosecond response of the detector. So we cannot use photodetectors to measure such short pulses. We can measure nanosecond pulses with the photodiode. So when we have a nanosecond pulse, we put it on the detector, and the output of the detector will be also a nanosecond pulse, which corresponds to the shape of our optical pulse. But in case of very short pulses, this wouldn't work. However, as I said, we can use the pulse itself. And this is called optical autocorrelation. And I will show you just in a minute. And there are two more advanced techniques that can measure the pulse duration. The one is called FROG, which stands for frequency resolve optical gating. And another one is SPIDER, which stands for spectral phase interferometry for direct electric field reconstruction. And the autocorrelation is generally a much simpler way of measuring pulses. So this is the simplest method. And these two are more advanced. But I will explain you that on the example of an autocorrelator. And I will also briefly maybe say a few words about these two other methods. So in autocorrelation, we use the pulse itself to measure its duration, right? So we use the replica of the pulse. So we use a Michelson interferometer for that. So this is a Michelson interferometer where the input pulse is split into two replicas. So these are two identical replicas, and they are directed to two mirrors. And then these replicas, after passing through this path and being reflected by these two mirrors, they meet again on the beam splitter here and interfere together. If the paths here, the optical paths here and here are equal, then the pulses will interfere, right, constructively, because we have the same distance. but we put one of the mirrors on a time delay on a shaker. So we just move this mirror back and forth. We just translate it. So it is moving continuously from one direction to the other one, right? So we provide some kind of the sweep between these two pulses. So it means that these two pulses will that are overlapping here on this beam splitter, they will at some point they will overlap, but if the shaker moves the mirror away from the, let's say, matching point, then we will see no interference, right? So it means that we will see the interferometric signal only in the case where the pulses were somehow overlapping with each other, right? So when they overlap like that, we will see that there is some interference between them, right? If they will overlap like that, we will see a lot of interference signal. But if the delay moves the mirror away from this overlapping of the two pulses, they will just miss each other and they will create no interferometric signal, right? So we put a crystal for the second harmonic generation. This is the same crystal that is used for frequency doubling of laser light. I already mentioned about making the green laser out of the infrared laser. So this is just to make sure that we see only these overlapped pulses, because two separate pulses will not create a second harmonic. Only the part that is overlapping will create it. So when the pulses are overlapping, they create a signal that we observe on the photodiode. And the duration of the signal on the photodiode is proportional to the length of the pulse. Yeah, and this this output signal is registered on a time scale of, let's say, milliseconds, because this is given by the translation speed of the shaker. So it doesn't matter whether the pulse durations are 100 or 500 femtoseconds. We can measure it. And the signal that we see on the photodetector from this interference looks like that. So this is a typical autocorrelation signal. The rule of the autocorrelation is that we have some kind of offset here, and we have the intensity proportion is 8:1. So we have 8 times more signal here than here. So here we have 8. You should have 8 in the ideal case, and here we should have 1. And from this image, you can retrieve the width of the pulse, because we can measure the width of this autocorrelation. You can see on this oscilloscope that the time base is 200 microseconds per division. Okay, so it's microseconds. So how to convert to femtoseconds? Because I said that this is a femtosecond pulse. So we need just to count the fringes that we have here, because basically this is just a sinusoidal signal. It consists of peaks. So we just need to count these peaks, and by knowing the wavelength of our laser and by knowing the velocity of light, and applying some constant factor for either whether it's a Gaussian or hyperbolic second pulse, we can calculate the pulse duration. So this pulse here will correspond to approximately 100 femtoseconds, I guess, but I would need to calculate that. But there are like tens or hundreds of these maximas, so we just count them and we can retrieve the pulse duration from this measurement. So there are autocorrelators available commercially. So you can just buy laboratory devices like this here. So you have the optical part, you just couple the light here into this hole, this input aperture, and you have a controller that just plots you the pulse and reads out the pulse duration. You can also build the device by yourself. This is one of the homemade design. So there is a beam splitter, one retroreflector, second retroreflector. This is placed on a shaker. It might be even a loudspeaker, but this is a shaker. So it moves this mirror. And here we have the detector and some electronics to plot the pulse on the on the screen. So a more advanced device is the so-called frog. So the difference between the frog and the autocorrelation is that in the autocorrelator, we use a detector. So we observe the signal using a photodetector. So we have just a photodiode. But in the frog, we use not a detector, but we use a spectrometer. So we also get information about the spectrum of the pulse. So the principle is the same. So we also divide the pulse into two replicas with a beam splitter, and we have a variable delay. And then we overlap the two pulses on the crystal, on the nonlinear crystal, and observe the field on the spectrometer. And by doing that, we can, by registering the spectrum as a function of time, so we just record the evolution of the spectrum in time. So we get some so-called 2D frog spectrograms. So how does the evolution of the spectrum of the pulse look like in the time domain over the duration of the pulse? So from this image, we can retrieve the pulse shape in the time domain and retrieve the spectrum, of course, right, of the pulse. And we have also access to the phase of individual spectral component. So if you want to know some more details about frog, I can recommend you reading the book of Rick Trebino. He is the founder, one of the founders of the frog technique. He wrote a very nice book about measurements of short laser pulses. But the difference between the frog and the autocorrelation is that the frog will give us information about the spectrum and about the phase of the spectrum of the spectral components of the pulse. The autocorrelation gives us only information about the width of the pulse, while the frog can retrieve the actual pulse shape and also the spectrum of the pulse. Yeah, this is the example of the frog that we have in our laboratory. So we have a frog device that just can retrieve the spectrum here, retrieve the pulse duration, and also measure these two-dimensional spectrograms. And in this example, you have a 59 femtosecond wide pulse. Yeah, and the third device is the SPIDER. So this is the spectral phase interferometry for direct field reconstruction. This is a more complicated device. However, it's much faster than the frog, because the frog needs some iterative algorithms to retrieve the shape of the pulse, but the SPIDER is kind of a straightforward, so it's much faster. And it's also available as commercially available devices that you can just put on the optical table and measure pulses. Okay, if you have any questions, then of course write it or interrupt. So to summarize the features of the pulsed laser, as I said, we define the pulse repetition rate. Right, so this is the spacing between the pulses. We define the pulse peak power and the pulse duration. And we already mentioned about mode locking, which is one of the ways of making the pulse laser. However, there are other mechanisms how to make the laser pulsed. And if you look at this image, you can already see that this is just a simple modulation of the amplitude, right, of the signal. So an easiest way to make a laser pulsed would be just to take a modulator and just make pulses, right, out of it. So this is actually possible, and the modulation of optical signals has a very long history. So as you can see, this guy is modulating somehow the optical signal to communicate with his colleagues, which are located somewhere else. And in lasers, it looks pretty much the same. So we already described the mode locking. However, I'd like to introduce you to two remaining techniques. One is so-called gain switching, and the second one is called Q switching. And these are techniques that are based purely on just modulation of the laser parameters. So to make the laser pulsed, the first guess would be, yeah, just put the modulator at the output of the laser, right? So we have a continuous wave laser, so we have a continuous output here, and we just put a modulator which just acts as a shutter, and we just slice the output to have pulses. And this is fine, but the pulses will have the peak power, which will be on the same level as the continuous wave power of the laser, right, in this case. But in the second case, if we move this modulator inside the resonator, so you see, this is, we would say, intracavity, because this is inside the resonator, then this completely changes the situation, because then we can have a peak power which is much higher than the average power or the CW power that would be generated from the laser. This is because if we insert this modulator inside this resonator and we pump the laser, right? So we deliver energy, and the modulator is closed, so if the shutter is off, so the modulator is not is blocking light. You cannot pass any light through the modulator. It means that you are storing a lot of energy in the gain medium because you still pumped, but the gain medium cannot release the energy in the form of the laser beam because it's blocked here. But then suddenly, if you open the modulator, you can release a huge pulse at the output, right? And this is happening here because the peak power of the pulse is much higher than the corresponding CW power, or the actually average power that is generated by this laser. So I didn't mention, but for example, in mode locked lasers, if the average power is at the level of 1 milliwatt, the peak power can be equal to, for example, that depends on the repetition frequency, but for example, 400 watts. So you can see what is the difference here. So it also means that if I would make a laser that has an average power of maybe kilowatts, I could get peak power of petawatts or terawatts or petawatts, right? So enormously high peak power. So the first method of making the pulsed laser, as I mentioned here, is gain switching. So gain switching works. So the principle of gain switching is shown here in this image. So we modulate the pump. Okay, so gain switching is forced by controlling the pump laser. So we just turn on and off the pump laser. So it might be the flash lamp, it might be the laser diode in solid state lasers, or it might be, we very often use gain switching in semiconductor lasers, where we just switch the current that is used to drive the laser, right? It's mostly used in semiconductor laser. So it means that we have no modulator inside the laser. So you can see we have our resonator, we have only the gain medium, but we apply amplitude modulation, pulse modulation to our pump beam. And it turns out that the output pulse of the gain switched laser is shorter than the pump pulse and has a much higher peak power. Because this is resulting from the dynamics of the gain medium, but when we pump our laser with a pulse, when we start switching off our pump, here we start switching it off, then our output activates. So the pulse is being released from the laser. So we have an output pulse here, the red one, and the peak power is, as you can see, much higher than the peak power of the pump pulse. You might be wondering how, but generally the energy is conserved here, as you can see, because the pump pulse was much longer, because the gain medium was storing the energy because of the long lifetime of the of this energy level here. So it was storing the energy, but then suddenly it just released the energy in the form of a very short pulse. So the transient dynamics of this kind of device is shown here. So this applies to, this is as an example of semiconductor laser, but this applies to other lasers as well. So in semiconductor lasers, you can see that when we run a pulse to the current that is driving our laser, we increase the carrier density in the semiconductor, and we at some point we exceed the threshold for lasing, and when we reach a value of the maximum carrier density, then the laser starts emitting a pulse, right? And then we can turn off the current pulse, and the pulse will be released from the laser. There can be, of course, some modifications to this profile of the pulse, so you can make kind of a pedestal here, which can further shorten the pulse. So you see that the pulse here is shorter than the pulse here, and it has a higher intensity. So this is a semiconductor laser with gain switching. This can be also applied to fiber lasers. So you see here in this example, we have a ytterbium doped fiber laser. This is a Fabry-Perot resonator with 2 fiber Bragg gratings, FBG. So these are mirrors that are Bragg mirrors on the fiber. So this is the resonator, and we have the pump, and the pump is driven by a rectangular signal. So we modulate the pump. And here on the bottom, you can see the images of the temporal oscilloscope traces of the pump pulse and the actual laser output pulse. So you can see that the pump pulse is long and it has a relatively low peak power, but the output pulse is much more powerful because we have a few hundreds of watts, and the pulse duration is much shorter. So the energy is stored over a very short period of time, shorter than in case of the pump pulse. And the third method of making pulsed lasers is so-called Q switching. So this is the method that we are applying a modulator inside the resonator. So we just put a modulator. This might be a acousto-optic or electro-optic modulator, and it is placed inside the resonator, and we apply a signal to drive this modulator. So we just modulate the losses of the cavity. So the pump is delivered constantly. So this is a continuous wave pump. So we constantly pump our gain medium. Therefore, the energy is stored in the atoms in the form of some kind of population inversion, which is accumulated in the gain medium. But then when we turn on the modulator, so it starts to be transparent, then the accumulated difference is released, and this generates this intense pulse. So typically the pulse duration is at the level of nanoseconds, sometimes up to microseconds. And the repetition between these pulses corresponds to the repetition to the frequency that we are driving our modulator, right? So the dynamics looks like that. So again, we at the beginning we have the losses higher than the gain, okay? But then we turn on the modulator, so it starts to be transparent. So we have less losses. And after some time where we have less losses, the pulse is released. And there exists also two types of Q switching. So one is active, or where the modulator is driven by a signal, or we can have also passive Q switching, where the modulator is a passive device. But in most of the cases, we use active Q switching because it's more controllable, right, process. And if you Google the word Q switch laser, then in most of the cases you will see images like that. So it means you can already see that Q switch lasers have a lot of applications, also in materials processing, but also in dermatological procedures. So for example, tattoo removal here or here, here, or some dermatological procedures like some caring of some skin problems and so on. So these kind of systems can be found in when you go to the doctors. But this is not the only one application of Q switch laser, but one of the most widespread, because Q switching enables quite easy and cheap and controllable modulation of lasers. So obtaining controllable pulses with short duration, but not too short, and large energy and peak power. So this is in a scheme of that I have taken from the literature with a actively Q-switched laser with an electro-optical modulator. So we have a neodymium laser. So this is a neodymium crystal here. And we have a Pockels cell, which is an electro-optic modulator. So this is the electro-optical modulator. And we have a mirror here and a mirror here. So the modulator is just driven with the signal. And at the output here, we have pulses. Okay, so generally that's all for today and all for, let's say, my part of this lecture, of this course. So thank you very much for the attendance and for all the questions and for listening. In the next week, we will have the test, and the second part will be given by Dr. Paweł Kaczmarek. He will speak about optical fibers and fiber lasers and everything related to optical fibers in laser technology. I have sent you all the details about the test, but if you have any questions, either regarding the test or regarding the lecture, that's the great moment to ask now. Do you have any questions? Yeah, the question on the chat, is it possible to get some control question for the test? Yeah, I assume you have contact with your colleagues from previous years, and you can you can ask them for questions. But yeah, as I said, there will be maybe 2, maybe 3, but I think maybe 2 questions where you have to write something. So like, please write explain the principles of operation of a laser, like helium neon laser or CO2 laser, and then you have to just write on maybe 1 page the schematic of the laser, the energetic level structure, and just describe in a few sentences how this process occurs and how this laser works, or yeah, something like that. And then you have the test part where there are ABCD questions. So this will be just easy questions like mark the correct answer. So like, what is the wavelength that is emitted from the neodymium laser? And you have 4 wavelengths given, and you need to select the correct answer. So it's like that. So nothing very difficult, I think.
And how long will be this test?
Yeah, I think we should finish within like 40 minutes. So I will display the question on the slide, and you will have like 7, 8 minutes, maybe 10 minutes for writing for this particular question. Then the next question will appear, and you have another 10 minutes. And then I will display the test questions, and they will be appearing for like 1 minute on the screen, and you have 1 minute for answering the test question, and then we move forward to the next questions. We cannot go back to the previous questions. We cannot stop the time because we cannot stop the time. Time is flying. we don't have the power to stop time or to slow the time. And then maybe there will be a question to do some basic calculations, like, for example, calculation of the bandwidth, like switching between the bandwidth in wavelength and the frequency domain. So it seems that it will be like 30 to 40 minutes at maximum. Do you have any other questions? Okay, if no, then thank you very much once again. It was a pleasure for me to give you this lecture to you. And I am, of course, happy to answer all the questions if you have any questions in the future during the consultations or email, Zoom, phone, or anything you want. So thank you, and see you next week. Please remember about the cameras, because I need to see you when you're writing.
Goodbye.